Screen. Okay, I think you can all see my screen now. So welcome everybody to the April meeting of the Stockton Astronomical Society. And I wanted to look forward to a great presentation this evening with you. And then we'll have some announcements, and then we'll be able to share a little bit. The meeting tonight is Zoom only. And don't worry, we're not going to stick with this format. It's not the good old days of the pandemic where we're on Zoom all the time. But for this one meeting this month, we decided to stay with Zoom since so many folks were traveling for the eclipse. But we'll be back in hybrid mode, both Zoom and out at the San Joaquin County Office of Ed in May. So with that, let me go ahead and introduce our speaker this evening. Let me introduce Robert Reeves from San Antonio, Texas. Welcome, Robert, and thank you for being with us.
My pleasure.
Robert is an accomplished deep sky astrophotographer, and his current passion is repopularizing the moon within the amateur astronomy community by explaining the origin of the moon, the evolution of its face, and introducing its geology to moon lovers everywhere. Robert has perfected imaging techniques that allow the amateur astronomer using modest equipment to exceed the quality of the Earth-based lunar photographs taken during the Apollo era. In 1984, Robert began publishing articles about astronomy in various astronomy magazines. And since then, he has published over 250 magazine articles and newspaper columns about astronomy. Robert's latest book, Exploring the Moon with Robert Reeves, was released in August of 2023. And we're looking forward to hearing more about that book during your presentation, Robert. So please join with me in welcoming Robert Reeves to the meeting this evening. And with that, I'll stop sharing my screen and turn it over to you, Robert.
Okay, well, I'll share my screen and see what happens here.
Oh, and while you're doing that, Robert, would you like to take questions through your presentation or at the end?
Let's do it at the end so we can just go through the thing in one shot without well, me losing track of what the heck I'm saying, and keep the continuity of it. And then okay. So says I am sharing screen. Can you see my title slide?
We can.
Good. Okay. Now why isn't it going to? There it goes, full screen. Well, let me back up one slide. You said you were looking forward to hearing about the book, so I'll throw out the 10-penny commercial right off the bat. And Exploring the Moon with Robert Reeves, I very pretentiously added my name to the title to separate the Exploring the Moon from the other dozen books that have the same title. It's available on Amazon. Just do a title search. Exploring the Moon with Robert Reeves. It'll pop right up. It's available in Kindle, paperback, and hardback. 300 pages, non-technical. I walk the novice into the moon and introduce them to the moon and make them a lunar authority within 300 pages. 422 illustrations, 44 full-page illustrations. All of the moon pictures in here, with the exception of the cover, were taken from my observatory on top of my garage out in the backyard. I've imaged the moon through various telescopes, a Skywatcher 180 millimeter Mac, a 50-year-old Celestron 8, Celestron 11 Edge HD, a Celestron 14 Edge HD, and I've also used a Skywatcher 20-inch Stargate Dobsonian. And you think an F4 Dobsonian is not necessarily the best instrument for the moon, right, imaging the moon, but actually it works really darn good. So I was real pleased how they turned out. So if you use the link shown at the bottom of the page, the Amazon link, bear in mind that the second character in the alphanumeric sequence there is a 0, not an O. So you end up at the right place. So moving into the rest of the presentation, I call my presentation Postcards from the Moon. It's a variation of a presentation that I've been giving for a number of years, including in person at the Chinese Academy of Sciences in Beijing back in 2019. So it's been around, this thing's been around the world, and it seems to be popular. So I don't mess with it all that much. Try and keep it like it is. Now, the whole premise of this thing is in the half century since the Apollo missions, much has appeared in the media about how we got to the moon, the politics of why we went to the moon, and the personalities who engineered, directed, and even flew the Apollo missions to the moon. But in the half century since humans last set foot on the moon, how much does the average person actually know about the moon? Well, the answer is surprisingly little, even among the amateur astronomy community. So I am out here to try and fix some of that. I've been in love with the moon my entire life. My earliest memories of the moon were watching moonrise through my bedroom window when I was a child. Now, today, space age explorations have not stripped the wonder and the mystery I felt for the moon when I was young. Now, there's an actual name for people like me, and before you even think of lunatic, the actual name is selenophile, a person who loves the moon. Now, over the past 20 years, I've spent an inordinate amount of time chasing big telescopes across the southern United States in order to take high-resolution lunar photographs. But, whoops, the irony of it is, I find I can take better pictures of the moon from my own observatory at home with 7 to 11-inch telescopes, because the poor seeing conditions that are prevalent here in Texas or South Texas, where I'm at, do not degrade the image in smaller telescopes as much as it does in large telescopes. So how good is modern lunar imaging with a modest amateur telescope? Well, the image on the right is a plate taken from the famous Kuiper Lunar Atlas. I have a copy of it. It was the best that professional astronomers could do from the Earth in the 1960s, before we started sending spacecraft to the moon. And the image on the left was taken from my backyard with a Celestron 11 telescope. They're both the same field. The Kuiper Atlas is south up, as per the convention prior to 1961. And the image on the left, taken from my backyard. I'll let you be the judge which one is better. Amateur lunar photography, planetary photography has come a long, long way. I like to say that I have no special talent. I'm only passionately curious. And if you are about any particular thing, over decades, eventually you learn a little bit about it. And I like to spread what I have learned and hopefully tweak somebody else's interest in this. So the moon is my playground, and I invite you to come out and play with me. Now, when I was young, the moon was a big deal. The moon was a dream, a goal, a destination, a place of mystery to be explored by brave heroes who dared to ride a pillar of fire and set foot on another world. But in the mid-1970s, there was a fundamental shift in amateur astronomy. The introduction of the 8-inch Schmidt-Cassegrain gave us a powerful, affordable, portable telescope, and it opened up the deep sky to amateur astronomers, and the moon kind of faded from our dreams. So my goal of this presentation is twofold: to bring the moon back within our astronomical realm, to make it not something to be avoided because it interferes with the deep sky, but to get you to look at the moon, not just to look at the moon, but to see it and understand it, to become friends with the moon. So today, many astronomers consider the moon boring, a place covered with bumps and holes. But the moon is not visually static. The moon is a geologic wonderland that changes day by day, even hour by hour. There's much to love, much to see on the moon once you know what to look for. I want you to go back to the moon with me and rediscover its wonders. So tonight we're going to look at the creation of the moon, the evolution of the moon's face, understand some of the various forms of geology we see through a telescope, and explore some sentimental lunar favorites that are favorites of both novice and experienced astronomers. Now, of course, the earliest event on the moon was necessarily the creation of the moon. And the current favored theory is a collision between two worlds early in the lifetime of the solar system. The proto-Earth fought for orbital supremacy about 4.5 billion years ago, ended up colliding. The proto-Earth and a small Mars-sized body that we now hypothetically call Theia collided and shattered. And from the debris of that collision, our friends out at Southwest Research here in San Antonio have run simulation after simulation, and invariably the same thing happens. The Earth formed, the heavy elements, iron and heavy elements coalesced into the Earth. The lighter, more silicate elements accumulated in a Saturn-like ring and eventually coalesced into the moon we see today. The moon accreted into a ball about the size of today's moon in a fairly short period of time. Within about a year to 100 years, the debris coalesced into the moon as we see it today. Now, the early moon was much closer to Earth than it is now. Now, when it coalesced and formed, it was probably no further away than the geosynchronous satellites are in Earth orbit right now. All of the communications and weather satellites that we rely on. Back 4.5 billion years ago, the molten moon, this science fiction vision of a glowing sphere of molten rock flying through space. We may play well in pulp science fiction, but in reality, the molten moon was probably a dark body with a chilled layer of solidified rock on its surface, insulating the inside. In this molten sphere, the iron and heavy radioactive elements sank to the middle, silicates floated to the top in a global magma ocean, and it took millions of years for the moon to solidify. Now, once the moon solidified, it entered a period of geologic epochs of time, much like well, when we were kids, we were fascinated with dinosaurs. We remember the strange sounding names like the Jurassic era, the Triassic, the Cretaceous period. Well, the same thing happened on the moon. It underwent a series of geologic epochs of time. On the moon, anything from the formation of the moon up to about 3.9 billion years ago was pre-Nectarian. And the dividing line is the Nectarian epoch, very short period, only about 100 million years. That was from 3.9 to about 3.8 billion years ago. During this time, the alignment of Jupiter and Saturn, their orbits shifted as the solar system was settling in and getting to where it was stable. The orbits of Jupiter and Saturn entered a 2-to-1 resonance, and the gravitational interaction showered the inner solar system with thousands of comets and asteroids. And during this time, the moon underwent what we call the late heavy bombardment. Well, the Earth, Mars, Venus, Mercury all underwent the same bombardment. During the Apollo era, we didn't realize that. But in the 1970s, we started sending spacecraft to Mercury, to Mars. Eventually, we sent spacecraft to Venus that had radar that penetrated the clouds, and we found craters on all of these worlds. Mars, very heavily cratered. We found that out earlier with the Mariner program. Later in the 70s, we sent Mariner 10 to Venus, found that the Mercury looked essentially like the moon. And of course, Venus, very heavily cratered under its cloud cover too. Only the Earth doesn't have these craters. All the other worlds still retain them, including the moon. The Earth is unique. it has oceans, it has weather, it has plate tectonics, it has ongoing volcanism. So it repaves its surface and erased all of these fierce impacts. Today, through a modest amateur telescope, the evidence of the collision carnage of the early solar system is only visible on the moon. We can't see details on the other planets with sufficient resolution from Earth to see this, but on the moon we can. So progressing on from about a little over 3 million to 3.85 million years ago, we call it the Imbrium epoch. And this was when most of the volcanism occurred on the moon. The giant basins created by the asteroid collisions, the very low-lying ones that filled in with basalt, lava flows. Then we entered the Eratosthenian epoch from about 1 to 3 billion years ago. This is when many of the post-Mare craters were formed. And then finally we get to the modern era, the Copernican epoch, from about 1 billion years ago to the present. And any crater on the moon that possesses a ray system is a Copernican epoch crater. We can specifically date these craters as Copernican because after about 1 billion years, ray systems fade because of the constant meteoric bombardment, tilling the lunar soil, creating regolith, and erasing the rays. So the moon, everything on the moon is dated by either being pre-Nectarian, Nectarian, Imbrium, Eratosthenian, or Copernican, very distinctive periods of time. So looking back to almost 4 billion years ago after the late heavy bombardment, this is pretty much what the moon looked like. Crater upon crater with massive basins where the giant asteroids struck. And you can begin to recognize the pattern of some of these. You see where eventually they would fill in with lava and form the face of the moon. Very distinctly up at the upper left, we see the Imbrium Basin. Next to it, the Serenitatis Basin. Over on the left, the Chrysium Basin, which, filled in with lava flows during the Imbrian epoch and created the dark features that we now recognize as the lunar maria that create the face of the moon that we see, the man in the moon that we see during the rising full moon. And then the current epoch, Copernican epoch, from about 1 billion years ago to now, all of the rayed craters now are visible and add a little bit of observational spice and personality to the moon. Now, you need to understand there are only 2 primary landscape forming processes on the moon. Everything we see on the moon through an eyepiece was either created by an impact or by volcanism. The Maria, dark regions, volcanic, basalt, relatively few craters on them, and they're relatively flat. The hylids are the original primary magmatic crust of the moon, primarily an orthosite, a single mineral with is primarily a single type of mineral, in this case, the silicate minerals that floated to the top of the original magma ocean on the moon. Heavily cratered, relatively rough, because it has not been flooded with basalt. These are highland areas that did not flood with basalt. So, looking at the moon just with the naked eye, you can see the large features on the moon, the maria, the lunar seas, as we call them. These are fields of dark basalt deposited by ancient volcanism. And the basins on the moon and the maria lying within them are not the same feature. We have to understand the basins were created by asteroid impacts. The maria lying within them were formed by lava eruptions flooding into these basins. And not all basins contain a maria. There are 70 some odd basins on the moon that have been identified. The backside of the moon has just as many basins as the front side, but there are almost no maria on the far side because the far side crust is thicker and it restricted volcanic eruptions. So the maria define the face of the man on the moon, the very caricature of the man on the moon that we see. There are 21 named maria on the near side. 11 were named by Giovanni Riccioli in the 17th century. 8 were named in the 19th or the early 20th century, and 2 were named in the space age. Indeed, the last one was named after I bought the house I live in right now. So the moon's face is a dynamic feature. It is still names being added to the lunar map. Now, the main theme of the Maria that we see from the Earth, we see Maria Nectaris, round. Whoops, go the other way. Chrysium, also round. The same with Serenitatis, or Mare Imbrium, the Sea of Rains. Mare Humorum, the Sea of Humidity. These dark basalt fields lay within these giant impact basins. And an impact basin is nothing more than a very big crater. Any crater larger than 300 kilometers in diameter is considered to be a basin. And well, the largest Mare on the moon is not called a sea, it's an ocean. Oceanus Procellarum, the ocean of storms, is twice as big as Mare Imbrium, but it's so foreshortened on the western side of the moon that it doesn't even contribute to the face of the man in the moon. It's 2 million square kilometers, so a million square kilometers larger than Imbrium, but it's almost insignificant when looking at it with the eye, because it's so close to the lunar limb and very foreshortened. Another lunar Mare that's unusual, Mare Austral, the southern sea. The Austral basin did not completely fill up with lava flows like some of the other larger basins on the near side of the moon. And that's because Austral is close to the far side of the moon. It's right on the limb of the moon. And the far side of the moon has a thicker crust, like I said, about 10 kilometers thicker than the near side. So it ended up being a collection of basalt flooded craters instead of a completely basalt flooded basin. And as evidenced by Mare Frigoris, not all Mare lie within a single basin. Frigoris spans the entire width of the face of the man in the moon, but only stands about 200 kilometers high. So it lies in portions of the Procellarum, the Imbrium, and the Serenitatis basins, and kind of forms the eyebrows over the man in the moon's eyes when you look at it with the naked eye. Now, lunar mountains, distinctly different than Earth mountains. Earth's mountains are continuously created by plate tectonics and volcanism, and are eroded away by Earth's weather and oceans and plate tectonics. Land is subducted, remelted in the interior, erupts again millions of years later. But lunar mountains are created by a different process. Lunar mountain chains, I mean. They are the result of an impact. Lunar mountain chains are the raised rim of the impact basins. Now, individual peaks can form at the center of large impact craters through a different process, but these mountain chains are the rim of impact basins. And these mountain chains have remained unchanged since their formation almost 4 billion years ago, whereas Earth's mountains can be significantly altered in as little as 100 million years. So some examples: the Alps Mountains up on the northern shore of Mare Imbrium, extending eastward from Plato, and we see the gash of the Alpine Valley cutting through the Alps. Over on the eastern side, the Caucasus Mountains. And further down along the southeastern rim, the Apennine mountain chain. And then at the south, just above Copernicus crater, the Carpathian Mountains. Now you'll notice that there's a theme here. Lunar mountains are named after terrestrial mountain chains, so they have familiar sounding names. Now, all 4 of these mountain chains are the eastern rim of the Imbrium impact basin. So there's your common theme. These mountain ranges, mountain chains, are the rims, raised rims of the impact basins. Now there's a rather lengthy mountain chain on the moon called the Cordillera. You can only see it one day every lunar month. And that's because it's on the far western side of the moon. arcing around Mare Orientale. Now, it takes 13 days for the lunar phase to go from new moon to where sunrise finally reaches the western limb of the moon and starts to cast a shadow behind the Cordillera Mountains, which we can see running across the middle of the field of view. Behind the Cordillera are the Rook Mountains, also casting a shadow. And then right on the horizon, we see another mountain chain protruding into the sunlight. It has no official name, but we unofficially call it the Inner Rook Mountains. Now, these mountains are the impact rings surrounding the Oriental Basin, which is right on the limb of the moon, so close to the edge of the moon that, depending upon libration, sometimes it's on the far side of the moon, sometimes it'll rock around where we can see it in its entirety and see the far side of it, because the moon rocks back and forth, nods up and down because of its elliptical orbit. And we can end up seeing a total of 59% of the moon's surface. But we have to wait a while for the effects of this libration to show all 59% of it, because sometimes the part that's tilted toward us is in shadow. So it takes about 7 years, six years for the entire other 9% of the far side of the moon to reveal itself. But as I was saying, we only see this one day a month. 12 days into the lunation, it's still in shadow. On the 13th day, the sun is high enough that it's throwing shadows, letting us see these mountains. But on the 14th day, full moon, these shadows disappear because the moon is very flatly illuminated, and the Cordillera are no longer visible because we can't distinguish them without the contrast enhancing shadows. Now, some prominent mountain chains on the moon, such as the Western Crisium Basin impact ring, they're unnamed. There's an amazing number of features on the moon that are unnamed. And I've lobbied heavily with Chuck Wood. You recognize the name. He's the lunar columnist in Sky and Telescope, but he is also the head of the IAU Lunar Nomenclature Committee. So he and I have had some discussions about various things that I think should be named on the moon, but he's the boss and I lost. So moving on to craters on the moon. There are many different types of craters. They're not all just holes in the ground. So let's review this. Craters are classified what we call the crater main sequence, to borrow a term from stellar astronomy. But the sequence is much shorter for the moon. Any crater smaller than about 16 to 21 kilometers in diameter is a simple bowl-shaped crater. The dynamics of the impact that create it will result in something that simply looks like you took a giant ice cream scoop and carved a divot out of the moon. But larger than 16 to 21 kilometers, the dynamics of the impact create what we call a complex crater. It has a central peak where the subsurface rock rebounds like a trampoline in response to the impact shock and freezes into a central peak. The crater walls are so large and so high, they don't have the structural strength to support themselves, and they collapse into the crater and form a series of terraces. And then, like I said before, if a crater is greater than 300 kilometers in diameter, we don't call it a crater anymore. It's a basin. Some examples: a simple crater like Helicon and Leverrier up on northwest Mare Imbrium. Complex crater, Copernicus. We get an overhead view of it from the Earth. Shining example. A basin that did not fill up with basalt. An example is Bailey down in the southwestern limb of the moon, 302 kilometers in diameter. Originally classified as a crater, but now we know we have a different classification scheme now. So now it is Bailey Basin, although it retains by legacy the name Bailey. Complex craters, like I said, feature a central peak and collapsed terrace walls. Many examples on the moon: Pythagoras up in the northwest, Boreas down near the South Pole, Geminus up above Mare Crisium. Now, crater rays, they look like these snowflakes splashed out from the some of the newer craters on the moon. Crater rays are composed of pulverized glassy material thrown from the crater by the explosion that created the crater. Like I said earlier, crater rays fade after about 1 billion years, and they're an indication that the parent crater is fairly young, less than 1 billion years. So rays are brightest near the full moon because this ray material is very efficient at reflecting sunlight back toward its source, which is the sun. And at full moon, the Earth is between the sun and the moon. This glassy material that makes the crater rays, very similar to the material that are on highway signs. You've gone down the interstate and you can read a sign with your car headlights. You can read the writing long before you can distinguish that there's an actual sign there. The reflecting material is reflecting the light back at you before the sign itself is illuminated. Crater rays react in a similar fashion. And there's different types of rays as well. Not all of them are splashes like a snowflake in all directions. Monodirectional rays, such as those extending from the craters Messier and Messier A, and the butterfly ray pattern, like the ones extending from Proclus on the right-hand side, are an indication of a very oblique impact. In this case, we're talking about impacts that can be as shallow as 5 degrees or less. In this case, no ray material splashes back in the direction the impactor arrived from. The case of Messier, up at the upper left, the right-hand one is Messier. The impactor struck, splashed out this lateral splatter of rays that we call a butterfly pattern, ricocheted, went 20-something kilometers downrange, struck again, created Messier A, and showered its monodirectional rays downrange. And then, of course, Proclus, another classic butterfly pattern, very distinct zone of avoidance in the direction that the impactor arrived from. Another class of craters are called secondaries. Now, they're created by ejecta thrown out by the primary crater. This material is blasted out of the moon's surface by the asteroid impact that created the crater. And if the velocity of the object being ejected by this crater formation process is greater than 2.4 kilometers per second, well, it escapes the moon completely and goes into orbit around the sun. Therefore, all secondary craters, the impact velocity of them must be 2.4 kilometers per second or less. And this is significantly less than the impact speed of a cosmic impact, or something that's been in orbit around the sun that strikes 20 kilometers per second or faster. Now, the majority of smaller craters, 20 kilometers or less on the moon, are believed to be secondary craters, but these secondaries can appear hundreds of kilometers from a primary impact. So sometimes it's pretty tough to associate a secondary with its parent crater. But in cases like Copernicus, it's very obvious. We have these radial streams and chains of craters, secondary craters streaming out from the primary impact. And this is very dramatic to see just in a backyard telescope. Now, not all craters are round. We've got a number of craters that are very elongated. Some of them are just simply merged impacts, like Haensel. It appears peanut-shaped because of our slanted perspective, viewing it down to the southern hemisphere of the moon, but it's 2 merged round craters. The same with Rata E, the keyhole-shaped crater, multiple overlapping impacts. But consider Schiller on the right. This is a single oblique impact. And to put Schiller's size in perspective, it is 170 kilometers long, only 1/3 as wide. And if you translated Schiller's length into the diameter of a round crater, Schiller would be among the top 10 largest craters on the near side of the moon. And continuing the theme of not all craters are round, here we've got Anaximander A and B pivoting off of Carpenter crater up at the upper left. Looks like a Valentine heart. Meton crater, lower left. Four uh, circular craters that have been merged by the deluge of ejecta thrown from the Imbrium Basin impact almost 4 billion years ago, obliterated the interior of the craters, and now all we see is this four-leaf clover pattern. Agrippa and Godin, very distinctly bullet and bell-shaped. There's craters on the moon that are hexagonal, octagonal, square. I'll show you a square crater here in a little while. Yet another class of craters, floor fractured craters. These started out as ordinary complex craters, collapsed terrace walls, central peak, but they form near the edge of a maria where there are subsurface magma chambers. And the impact that created these craters fractured the surface underneath the crater, allowing this magma to seep up and enter the crater from below, flooding its interior from the inside, pushing up the crater floor, elevating it, sometimes completely erasing the central peak. Gassendi, just north of Mare Humorum, a very prime example. I call it my oatmeal cookie crater because it looks cracked and split like one of grandma's oatmeal cookies right out of the oven. Posidonius of northeastern Mare Serenitatis, same theme. Raised floor, volcanically raised floor, rills and cracks across it. Atlas crater, extreme upper right, same thing. Ghost craters are craters that existed in basins before they flooded with basalt to become a maria. In this case, just north of the Apollo 11 landing zone, Lamont crater. We see it as a series of circular ridges that denote a buried impact structure underneath the basalts of Mare Tranquillitatis. And the radial ridges extending outward from it make it look like a big spider. Up near Copernicus, almost hidden in all of the Copernican secondary craters, we see the round form of Stadius, its crown just barely protruding above the basalt. And the same with Flamsteed P, which is on southern Oceanus Procellarum. We call this the Flamsteed Ring, 100 kilometers in diameter, and just the crown of the crater rim still protruding above the basalt fields. Catena, a technical term, Latin term for crater chain. This wasn't recognized as a lunar feature until 1976. And Catena is a series of sequential impacts created by the impact of a object that was gravitationally broken up by either the Earth or the Moon's gravity, and didn't hit as a single object, but rained down as a series of impacts. In this case, up Catena Mueller on the upper left, Catena Davy, just south of the Apollo 16 landing site, Catena Abulfeda. This one is almost 200 kilometers long, one of the longest crater chains on the moon. Another form of feature on the moon is a volcanic feature, wrinkle ridges, known by the scientific Latin name of dorsum or dorsa in the plural. And these are folds on Mars surfaces where sheets of basalt have crushed together and buckled into a lengthy ridge that rarely exceeds a couple of 100 meters in elevation, but they can be very long, extending for hundreds of kilometers. And typically, the named wrinkle ridges are named after Earth scientists. And the most popular wrinkle ridge shown in the picture on eastern Mare Serenitatis is the Serpentine Ridge. This is a combination of the lengths of both Dorsa Smirnov and Dorsa Lister. And they kind of twist together and form this long ropey chain on the just off the eastern shore of Mare Serenitatis. Very dramatic at sunrise, but you have to catch these just at sunrise because they're so shallow that when the sun gets pretty high, the shadows disappear then you can't see these anymore. You have to have the sunrise or the sunset shadows to see these features because they're only several hundred meters high. Another popular wrinkle ridge, Dorsum Hine, on the western shore of Mare Imbrium, and notice the unnamed wrinkle ridges that look like frozen ocean waves washing into the Horseshoe Bay of Sinus Iridum up on northwestern Mare Imbrium. Another form of volcanic feature on the moon are rills. These are scientifically known by the Latin of rama or rime, if there's more than one. And these are grooves or channels of the moon that are appreciably longer than they are wide. And these are formed by three different processes, but all volcanic. Straight rills, such as Rama Hesiodus at the bottom, Rama Sursalis on the right. These are caused by the slumping of land between two parallel faults. And what happens here is the crust is split open by a volcanic dike, which is a vertical sheet of magma that pushed up from the moon's molten core, but it didn't breach the surface as a volcanic eruption. It just simply cracked the surface, and the land collapsed and created the rill. They can you can see rills split and running through pre-existing features. They will split a pre-existing crater, as well as the land around it, or they can be overlain by a later forming crater. Arcuate or curved rills are created by the stretching of land near the edge of a maria. In this case, the mass of the Mare basalt slumps toward the center of the basin. And as it slumps toward the basin, it pulls and stretches the shoreline and pulls open these curved rills that parallel the shoreline. In this case, Rima harpalis looks like a giant cat scratch around the eastern rim of the Humoran Basin. Now, sinuous rills are formed by flowing streams of molten lava, much like channels are cut in the earth by flowing water. In this case, molten lava meandered through this channel and emptied out onto Palus Putudinus on the western side of the Apennine Mountains. And in this case, this is also the Apollo 11 landing site, Rima Handley. Apollo 15. Apollo 15 landed just off to the right of the far right reach, actually the northern reach of Rima Hadley. And Dave Scott and Jim Irwin motored around there for 3 days in the first lunar rover on the moon. I had the great pleasure of talking to Dave Scott about his mission once in Tucson, and I told him quite frankly, Apollo 15 is my favorite lunar mission, and he said, well, strangely, his too. Of course, he was the pilot. Now, scarps on the moon are scientifically known by the Latin of rupes, and these are formed by two different processes. Some scarps are the surviving rim of an impact basin, as in the Rupus Altai that we see illuminated in sunrise here. The arcing long cliff-like structure spans over 400 kilometers on the southwestern side of Mare Nectaris, or the Nectaris Basin. Mare Nectaris itself out of the field of view, but this is the only surviving section of the outer Nectaris impact ring. And other scarps are created by the slumping of land on one side of a fault, such as Rupus Cauchy, the lower southernmost of these two parallel features. The upper one is Rima Cauchy, which is a rill. It's fairly shallow, probably about 50 meters deep, but Rupus Cauchy is a slope descending from one side, north side, down to the south side. And evidence of volcanism in the region. Notice the little two tiny volcanic domes down below Rupus Cauchy, one with a little caldera on the top. Now, the most famous a name just popped out of my head, just went away. Goodness. Anyway, the most famous cliff on the moon, Rupus Recta, straight wall. Back before the space age, before we went to the moon or put satellites in orbit of the moon, charted it in extreme detail. It was popular to depict straight wall as this sheer, imposing straight cliff, but it's not actually. The shadows fool us. At sunrise, it casts this rather lengthy shadow, and it makes us think that it's a very high cliff. But as the sun goes, nope, I think I'm ahead of myself on my slides. But as the sun goes over toward the west and illuminates the face of it, it becomes a white line feature as the cliff face is very brightly illuminated. And straight wall turns out to be a somewhat of a slope, not a cliff at all. And it descends about 300 to 400 meters over a rather wide area, broad area. So I think in the future, a spirited astronaut would be able to descend this on foot very carefully. It's a slope no more than 20, 25 degrees. So steep, but not impenetrable by any means. Past volcanic on the moon is evident in the form of pyroclastic deposits, sinuous rills like the Alpine, the Schroeder's Valley. We see a massive rill running through the middle Aristarchus Plateau, ash deposits around cinder cones, and volcanic domes, very similar to what we just saw. An example of pyroclastic deposits, this heart-shaped mountainous region just north of Rima Hygitus. You see it's distinctly darker. It's been dusted by volcanic ash that erupted out of fire fountains from the volcanic pits along the Rima Hygitus. And the region is basically heart-shaped, and it happens to be very close to the very center of the moon's disk. So I call this the heart of the moon. Ash deposits are also seen around cinder cones inside of Alphonsus crater, very near the center of the moon's disk. And in this case, look at the 9 o'clock, the 3 o'clock, about 5:30 positions, and you see the dark ash deposits around the volcanic pits. Other volcanic regions, the Marius Hills on Oceanus Procellarum. These are volcanic domes or bubble-like swelling, small shield volcanoes where highly fluid lavas formed low pancake-shaped structures. Marius Hills, about 250 of these scattered over about 70,000 square miles on Oceanus Procellarum. And then a little further north, we see Mons Rumker, about a half-kilometer high volcanic mound, topped by about a dozen other small volcanic domes. And Rumker, for many centuries, didn't get its due justice. It was miscategorized as a crater, although it clearly protrudes above the moon instead of indents it. But to me, it looks for all the world like a wad of chewing gum stuck to a parking lot. So, but Mons Rumker needs a little bit more love. It needs some respect. Now, putting all of these features together, let's look at some sentimental lunar favorites that everybody's going to love, whether you're an experienced lunar observer or a novice. One of the first things at first quarter you're going to notice, Plato crater. Doesn't look like a regular crater. Craters are supposed to be holes in the ground. This one is flat, black, covered with basalt. So it immediately catches our attention. It's on the northern shore of Mare Imbrium, Mare Frigoris just above it, north of it, the bird nest shape of Cassini crater down to the south of it. I mentioned that we can see square craters on the moon as well. Here's W Bond, very distinctly square-shaped crater. Almost looks like an old fortress structure that you would find out in the desert. Very square walls surrounding a fortified region. Getting closer to Plato, now we begin to see its surface isn't quite perfectly smooth. There's some small pits, 3-kilometer diameter craters within it. If you can see these little craters inside of Plato, you've got some good seeing going on. Enjoy the night. It's rare, or at least around here. And Plato is nestled in the Alps Mountains, down south in the on the northern regions of Mare Imbrium. Little Mons Pico and Mons Piton poke up through the basalt, and these little mountain peaks become very beloved by observers. The one that I'm particularly interested in, look at that little hammer-shaped thing. I call it Thor's hammer. Agent Coulson was looking for Thor's hammer for a long time. Well, it was right under his nose. It was laying on the moon. And getting even closer to Plato, now we also see details in the Alpine Valley to the east of Plato. And when you see that, excuse me, see that central rill running down the middle of the Alpine Valley, you've got some spectacular seeing going on. That rill is only about a half-kilometer diameter, in width, but it spans the 100-odd kilometer length of it. We can see linear features on the moon that if there were only a round object of the same diameter, we wouldn't see it. It's the same principle as from a long distance, you can see telephone wires. But if you tried to see an individual object, the diameter of that wire, you'd never find it. But linear features, even though they're smaller than what we should theoretically resolve, they show up very much like this rill in the middle of the Alpine Valley. And the rill has no name. One of those strange omissions. But just on the northeastern rim of the Alpine Valley, we see the shadowed pit of Trovolot crater. So if this rill is ever officially named, it will probably be Rima Trovolot. Tycho crater is another favorite. Mainly because of its spectacular ray system. It spans literally half the southern hemisphere of the moon. Now, Tycho is noticeably different than the other craters surrounding it. Looks very fresh, very young. Longomontanus, Clavius crater, others in the area, they're all about 4 billion years old. But here comes Tycho, the young interloper. It was formed only 108 million years ago, surrounding craters on the southern highlands. And one effect of that youth is the sunrise shot. Look closely in the territory around Tycho. Look at the hundreds and thousands of tiny pits that were carved into the surface of the moon by the shower of ejecta blasted out of the impact that created Tycho. Like I said, that's only 108 million years ago. So the flash of Tycho's creation likely startled many a T-Rex here on Earth. And again, another view, you can see the moon's surface almost looks like it's etched, almost rusted, with all the pits from the secondary impacts from the material thrown out from Tycho. Copernicus crater, up near the mid-latitudes of the moon. The early telescopic observers called Copernicus the monarch of the moon because of its massive ray structure that contrasts out on the dark Maria. Almost looks like this dancing snowflake. But Copernicus is also pretty spectacular at sunrise. The ray systems are not as evident at sunrise, but here we see Mare Imbrium just above it, Eratosthenes crater at the end of the Apennine mountain chain, which seems to point like a finger directly to Copernicus crater, the Carpathian Mountains, and secondary craters. We looked at them a little earlier, and how they spray out in chains and ropey trails radiating away from Copernicus. Just to the west of Copernicus, we see Ma'am, you're not muted. Well, this is very interesting. That's a new one on me. Okay.
I apologize for that.
Well,
I stopped the video.
okay. Let me know when to resume. Okay to start again?
Yes, yes, go ahead. Thank you, Robert.
Okay. Well, we'll just concentrate on other heavenly bodies. And I was saying Mare Insularum off to the west of Copernicus crater. Notice the hundreds of hills and bumps protruding above the basalt fields. This is a recently named Mare on the moon, named only in 1976. Mare Insularum, the Sea of Islands, and all of these hills protruding above the basalt are uh, look like islands protruding above the ocean. So they call it the Sea of Islands. And then just for artistic balance, we throw Reinhold crater down there in the bottom. Straight wall. I mentioned it earlier. Another sentimental lunar favorite that captures people's imaginations because it's different. It's not a crater or similar type feature. It just catches people's imaginations. On Western Mare Nubium, just south of our Zachel crater, Abit crater is the nearest named crater, but notice that there seems to be the structure encircling the straight wall. We see a horseshoe bay on the right-hand side overlaid by Thabit, where a large crater has been partially flooded with basalt from Mare Nubium, but out on the Mare itself, we see these wrinkle ridges where the buried outer rim or western rim of this unnamed crater reveals itself with these ridges. And this particular feature has no name, but it's huge. So Chuck Wood unofficially calls it ancient Thabit. Now consider straight wall at sundown. On Mare Nubium. The sun's going down in the west. The shadows are approaching across Mare Nubium, the wrinkle ridges becoming more and more dramatic. And you're an astronaut standing on top of that ridge on top of the straight wall, looking out at the sunset. When we look at sunset on Earth, the sun goes down, it touches the horizon, and you can almost set your watch 2 minutes later, that sun is going to be below the horizon. Well, the moon rotates much more slowly than the Earth. Watching sundown on the moon will take an hour. So gives you lots of time to contemplate the poetry and beauty of it. Now, wrapping this up, we'll look at a few nicknamed features on the moon. There's a lot of science names, a lot of legacy names that are cast in stone, but just like deep sky objects, where we don't call NGC 7000 by its official name, we call it the North American Nebula. The same with the Lagoon and the Trifid nebulas. We don't call them M6, M8, M20. You call out these nicknames, everybody knows what they are. Well, the same on the moon. There's a number of nicknamed features on the moon, and my good luck charm, I'd mentioned it earlier, Meton crater, the merged four craters that now create a four-leaf clover. So come on, keep hitting the wrong button. My lunar good luck charm. Chuck Wood calls the giant massifs on the Mare Imbrium side of the Alpine Valley the guardians. They look like giant Egyptian monuments guarding a pharaoh's tomb. Thor's hammer, I'd mentioned that. The T-shaped mountain ridges, originally known as Python Gamma, resembles Mjolnir, the magical hammer wielded by the mythical Norse god Thor. The Valentine Dome over on western Mare Serenitatis, about a 30-kilometer diameter, low pancake volcanic feature. informally, officially known as Linnae A1. We call it the Valentine Dome, but I'm not exactly sure where the name originated from because it doesn't look like a Valentine to me. It just looks like a pancake, but the name has stuck, so we're going to leave it like that. Cobra Head is the volcanic pit at the head of Schroeder's Valley. Millions of years ago, this fed molten lava that flowed hundreds of cubic kilometers of molten lava down the channel of Schroeder's Valley, emptying out onto Oceanus Procellarum. The heart of the moon. I claim this one, naming rights to it. The heart-shaped pyroclastic deposits north of the Rima Hyginus. And the lunar spider, Lamont, just north of the Apollo 11 landing site. The ghosts of Procellarum, the multiple ghost craters, craters that existed in the Procellarum basin prior to their being flooded by lava. And now only the crowns of those craters protrude through the lava as these circular ghost craters. So collectively, I call them the ghosts of Procellarum. And the railroad tracks, twin parallel rays that extend northwest from Tycho crater. Now, normally crater rays converge on the center of the crater, the explosion that created them, splatter out in all directions. But the railroad tracks, they do not converge. They're parallel. They're almost tangential to the rim of Tycho. And if you can figure out why, your name is going to be on a research paper somewhere. The Golden Handle, the Jura Mountains, which form the rim of Sinus Iridum up on northwest Mare Imbrium, as sunrise is breaking across the region before it completely illuminates Sinus Iridum. It starts to illuminate the rim of the Jura Mountains, and we call that arc the Golden Handle. And the Marius Hills, I mentioned them earlier, is not an official name. It's a nickname. The region has no name. All that collection of volcanic pits, or excuse me, that collection of volcanic domes is nameless in its own right. So we call it the Marius Hills. And then south of it is Reiner Gamma, that circular splotch with the whitish tail extending up about 170 kilometers. Call that the tadpole. And the Fireman's Hat, this volcanic, light-colored volcanic mound northeast of Gassendi crater. It's inverted, it's upside down, but it resembles a fireman's helmet. And finally, Huygens sword, which is straight wall with some other features. Notice at the south end of the straight wall, there's this hilly region that if you use some imagination, that hilly region looks like the guard on a sword, the hand guard on a sword, and then a feature called Stag's Head, this arc of a crater protruding above the basalt, we call it Stag's Horn, forms the sword's handle. So straight wall is the sword, the hills is the sword guard, Stag's Horn is the sword's handle. Collectively, we call this Huygens sword, named after Christian Huygens, who in the 1600s originally studied this region. So, in conclusion, I'd like to say that the moon is ever-changing. It is not static. The phases grow and shrink day by day. The shadows change hour by hour, as demonstrated in this series of 5 pictures, where over a period of only 2 hours, the interior of Ptolemaios crater revealed itself as the sun rose. Like I said, shadows change hour by hour. The moon is a geologic wonderland. There's so many different features on it, created by so many different things. Well, 2 basic processes, of course, but how they interact with each other, each one is almost unique. And the moon is accessible from our own backyard. The moon laughs at light pollution. The moon doesn't care if there's a light nearby or if the city lights or the city sky is bright. The moon is going to outshine it. So there is much to love on the moon, and I invite you to come join me on my playground and enjoy it. So I've enjoyed speaking with you, and I can take questions now if there are any.
Very good. Robert, thank you so much. Excellent presentation. Let's give Robert a round of applause for that. Thank you very much. And now if you'll just come off of mute, if you'd like to ask Robert a question, I'm sure you've got some questions or some comments after all those beautiful photographs. So who'd like to go first? Yeah, go ahead, Michael.
So, hi, Robert. My name is Michael. I am very much new
Hi.
to amateur astronomy. Your second slide, you were showing the epochs of the moon, and you had this date, and it said BY. What does the BY stand for?
Billions of years.
I see.
Billions. It's tough to think of objects that old, but on Earth, I mean, something ancient is thousands of years ago. You think of the Egyptians as ancient, or the other Pharaoh era of Egypt as ancient, but on the moon, these geologic periods are preserved and staring us right in the face. And we see features that were formed almost literally at the birth of the solar system, and they're still there. So when we talk about billions of years, it's a tough concept to wrap your head around, but we are actually seeing things that are that old.
Interesting. Okay, thank you.
You bet.
Eric, are you asking a question? You're on mute.
No, I'm telling my family's dog to be quiet. No, but I do have a question.
Sure.
Can you give an estimate on how much time it takes to cool the surface back down after the impact from a meteor? Like how much time does it take to form like the rim around the crater? Does it instantaneously cool down, or is it over a period of time?
Small craters, for instance, like when Tycho formed 108 million, not million years ago, the process was fairly quick. The amounts of liquefied impact heat melted rock was fairly small. It would splash up the crater rim and pool down back in the interior of it within minutes, and then start to cool off. So the complete cooling down of it, where it's at a stable temperature, was fairly quick, within days or months. So the moon gets incredibly cold when the sun goes down 200 degrees below Fahrenheit. So it didn't take long for a massive impact to cool down to reach a stable temperature. Unlike the original accretion of the moon, where the entire moon was molten, and it took millions of years for it to cool down and become solid enough to start recording the impacts on it, instead of them just mushing out and smoothing out again.
Thank you.
Sure.
I was wondering, you said the early moon was very close to the Earth,
Yes.
geostationary orbit close. That must have had a crazy impact on the tidal forces on the Earth, the crust and everything.
Yes, it did. It shook the Earth up just as much as we shook the moon up.
Right.
The moon didn't start receding away from the Earth until oceans formed. And it is the ocean tides that are slowly causing the moon to recede away. Unfortunately, I don't have that presentation on this company laptop, but up in Dallas, I gave a presentation regarding the eclipses that that had a slide to describe that. But basically, the moon pulls on the oceans, and we have a high tide on the moonward side. We have an equal high tide on the opposite side. But at the same time, the Earth is rotating. So these high tides are offset from the center line between Earth and the moon. Now, as this ocean tide is offset to one side, the ocean on the moon side exerts 7% more gravity on the moon than this ocean high tide on the opposite side of the Earth. And it is this gravitational pull of Earth's oceans that is slowly accelerating the moon. It's every orbit, the moon is a few millimeters higher than it was before, because the ocean tides are gravitationally accelerating it and forcing it further away. Since the Apollo missions, we've been able to measure this directly with laser reflectors on the moon. And we now know the moon is receding away from the Earth at 3.8 centimeters per year, just a little under 2 inches. So that means between now and back when Neil Armstrong did his small step for mankind, the moon is now almost 2 yards further away than it was when Apollo 11 landed.
Mhm.
So the ultimate effect is that as the moon gets further and further away, necessarily gets smaller and smaller. So it's a very curious thing that we are on the Earth and aware of what's happening on the sky. Humanity is here just when a total solar eclipse can happen. Before the moon was much closer. It occulted the much of the corona as well. In the future, the moon will be further away. All eclipses will be annular or even a transit of the moon across the sun.
Yeah.
But don't be too excited about total solar eclipses going away anytime soon. It'll be about 600 million years before total solar eclipses stop happening and the moon is finally far enough away that they're going to be diminishing. We're going to be enjoying lunar eclipses for a good while. I mean,
Yeah.
solar eclipses for a good while.
I was wondering though, with the tidal forces acting on the tectonic plates at the time when the moon was close, and it sounded like the moon was close for quite a while.
Oh yeah.
Are there any observable effects from that tectonic shifts that must have been going on with those from those tidal forces? Are any of those observable today?
Well, there's a lot of rills and cracks on the moon that
I
some
mean, on the
science.
Earth.
Oh, on the Earth? Not necessarily. Earth is very dynamic. It's
Yes,
always
yes.
moving around and repaving itself. But on the moon, some researchers have tried to come up with a correlation of rills and so forth, and come up with an idea of how the Earth might have expanded or contracted or shrunk or you know, basically shake and bake the moon. But I have really not made much sense out of that. I don't see any evidence of it other than ongoing moonquakes. Recent speculation about significant moonquakes near the South Pole because of tidal forces, and that will have a real impact. If it's real, it will have a real impact on the future of our moon base up there, because we want to establish the Artemis moon base near the South Pole, where it has access to the polar ices. And if that is a earthquake-prone area, might not be a good place to be landing one of Elon Musk's Starship with its rather narrow footpads. Be a bad day if that thing fell over. There's no
Wow.
Uber to get back home.
All right. Well, thank you. That was an awesome presentation. Appreciate it. And I think Michael down here has a question.
Sure.
Yes, great photographs, by the way, and great presentation. Actually, and I have an equipment question.
Sure.
I also look at the moon with a 102 millimeter Celestron refractor from the classics, and I was wondering, what's your choice as far as equipment, and how would a, let's say, 180 millimeter Max Sutov compare in that list of great equipment?
The 180 Mac, either as the Skywatcher version or the Celestron 700, they are the identical telescope, just rebranded, is an outstanding lunar telescope. When I first got it, it was the image quality was so good that I was comparing it as almost as good as my C11, which is a larger
Wow.
telescope.
Wow.
The image contrast is noticeably better. The resolution isn't quite as good because of the smaller aperture, but the image contrast is so much better that the images were very competitive. And for the price of the 180 Mac and a standard ZWO or QHY planetary camera, you have an outstanding sub $2,000 imaging package that's going to blow away anything the pros did back in the film era when that's how we did lunar photography. It's just an astonishing little setup. And very many of the images that I've shown today were taken with a 180 Mac.
Okay. Thank you. I appreciate that because I was looking at buying that for planetary and lunar work. So
Right.
you're helping to sell me to get one.
Yeah, well, it is an outstanding little instrument. I love mine.
Thank you.
Michael?
Yes, actually, just with that question from Michael, thank you, Michael. You just rung something in my head. What would you recommend as far as sites to observe for someone new to lunar observing?
Sites to observe, you mean objects on the moon?
Correct. Yes, sir.
Well, I could cheat and say, get my book and it'll show them all to you.
I was actually just looking on Amazon. Not even like a lie. I was actually looking on Amazon.
Well, the best place to look on the moon is, of course, along the terminator. It doesn't matter what phase it is. The terminator is where the shadows are, where the most detail is visible because of the shadows. Like I said, wrinkle ridges will disappear when the sun is too high. The small lunar domes will disappear if the sun is too high. So along the shadow line, whatever phase it is, that's where your best looking is going to be.
Okay.
Robert, I have a couple questions. I'll combine them. You mentioned the polar ice. Is there any evidence visually that we can see of that ice? And also, is there anything other than just the black and white photograph colors? Are there any colors that we can see on the moon through our telescopes?
Okay, ice-wise, we don't see it from Earth. The ice is in the permanently shadowed polar craters, where the sun, because the inclination of the moon's axis relative to the sun is only about 1.5 degrees. So these polar craters were perpetually shadowed. The temperature at the bottom of them, where sun never shines, is actually colder than the surface of Pluto. So they're invisible to us, but spacecraft in orbit around the moon have been detecting this ice for some time now. Color on the moon, people with really good color vision, not me, can detect various subtle shades, particularly around the Aristarchus Plateau up on the northern part of Oceanus Procellarum. That, even to me, it looks distinctly yellowish because of the volcanic deposits. But a popular thing that people are doing nowadays with color cameras is getting high bit depth images, like stack many frames with a planetary camera and get a high bit depth image so that the values on it can be stretched and bring out colors in the moon. And we get browns and we get various subtle shades of blue. The basalts on the moon, the varying amounts of iron and titanium give them a slight color, and people can enhance these colors easily in Photoshop. So the mineralogy of the moon, the mineral content of it, can be grossly determined by literally the color of the moon, the spectral reflectivity of it. And with modern lunar imaging and color cameras, we can do that now. Whereas the moon used to be basically a black and white object. The moon is so colorless to me that I process the image in black and white because it doesn't look any different to me. But the moon does have subtle colors that can be enhanced in Photoshop and brought out. It's not a natural looking moon, but it has scientific information in it that will tell you a little bit about the composition of the surface.
Very good. Thank you.
You bet.
Okay, folks, any other questions for Robert?
I have one more. Oh, go ahead, Michael.
No,
Oh,
I was about to say no. I don't have any more. You
Okay.
are free, Eric. Thank you.
One final question from me. Can you recommend any good planning tool, if there is such a tool, that would
Oh,
tell you like
definitely.
the best date and time to image a particular feature?
One thing that is the industry standard, so to speak, is a program called Virtual Moon Atlas. VMA, Virtual Moon Atlas. It's a free program. Um, just Google it. It's available from multiple places. It's been downloaded like 500,000 times. It is the gold standard uh, 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 for computer charting of the moon and doing calculations of libration and phases and so forth. Extremely good program, and I highly recommend it. And it will drill down to detail on the moon, down to tens of meters. It's extremely high resolution if you download all the additional data sets, like all of the lunar orbiter pictures, all of the Clementine images, all of the Chang'e images from the Chinese orbiter. They're all additional data sets that you can download that the program will access. And as you zoom in on an object, you get closer and closer and closer until basically you're down and looking at it on the NASA level. Very amazing program, and it is absolutely free, made by my friend Christian Legrand over in France.
Very good, thank you.
Mhm.
I've got one question for you. On the rills that were caused, the lava tube rills
Yeah.
caused by volcanism, are the cause of them almost always impacts or other?
Sinuous rills, which appear sometimes as collapsed lava tubes, or simple volcanic eruptions welling up from magma chambers under the moon, erupting and then descending downhill, where the lava flow carves the channel, and sometimes cooled lava paves over the top of it, and then the flows stop, and then the roof collapses, and we have the exposed rill again. But these are magma chambers, subsurface magma chambers that have simply erupted lava up through a volcanic vent. They're not an impact origin thing; they're a volcanic origin thing.
Okay, so they have to be billions of years old.
Oh yes, yeah. Hadley Rill probably hasn't flowed, or Schroeder's Valley probably hasn't flowed lava for 2 billion years.
All right, okay, that's kind of what I was thinking, is that because the moon crust has gotten so solidified that you wouldn't get magma coming up anywhere near the surface.
No, we think the moon has been essentially volcanically dormant for almost 1 billion years. There's a few spots on it where we see some challenges to that, where like a rayed crater, one of them, Lichtenberg, almost popped out of my head, but the crater Lichtenberg up on northern Oceanus Procellarum, it has a ray structure, but part of that ray structure appears to have been overlain by a lava flow. Now, the conventional thinking is rays fade after 1 billion years. Rays covered by a lava flow, lava flow must be less than 1 billion years. But it's one of those things that isn't a dead set fact. We're still kind of mulling that over, but the main drift is, though, that the moon has been basically volcanically dormant for about 1 billion years.
Okay, that's basically what the question was. Thanks.
Okay.
Well, excellent, excellent. Again, thank you so much, Robert. We appreciate it very much. Let's give him a round of applause, everyone. Thank you very much. Robert,
All right.
please stand by if you'd like to. We've got some
Whoops.
few announcements, and then
Ah,
I've got some
there.
photos of the solar eclipse. You might like to look at it with us. If you'll
Yeah.
stop sharing, I'll switch my screen to share.
There it goes.
There we go.
Finally quit. Okay, well, I've got to take care of some household chores. It's 10 o'clock at night here, so I've really enjoyed talking to you all, and I hope I've convinced some of you all to go out and look at that big bright light that blots out the deep sky.
Very good. We will, and we appreciate it so much. Thank you.
All righty.
Thank you, Robert.
Good night,
Thank you, Robert.
folks.
Great presentation. Good night.
Bye-bye.
Okay, I just have a few announcements. So if you can see my screen, tomorrow night, Delta College, I think the weather's going to be good. Doug, we need a few telescopes out there, right? With Delta College sky tours. If anyone's interested, if you need directions, reach out to us on the Yahoo chat. And we'll,
Tim, are you going to be able to make it?
I'm fairly confident I'm going to be able to make it. Yes.
Okay, because basically at this point it's you and I,
Okay.
unless anyone else can help out. All right.
Okay.
I'm still in Southern California, so
Right, I know,
won't be making it.
and Bill has a very good excuse not to. Bill cannot join us.
Okay. Well, Doug, maybe make some phone calls and see if you can round up at least one more scope, because sometimes you get quite a crowd.
I think I.
What was that?
Yeah.
Okay.
Okay. Then on Saturday night, astronomy in the park out at Oak Grove Park. I guess weather permitting, we'll look at the weather as that afternoon on Saturday and see if we're going to be able to hold that event. I would kind of look forward to it. And then Tuesday.
Okay. On that one, April 16 for Wickland. I got an email when I was gone in Southern Missouri, and we're gonna cancel that one.
Okay.
So strike April 16th at Mountain House.
Okay. And then put this on your calendar, everyone, to come out to Victory Park on April 21st and join us for Earth Day. Even if you don't participate as part of SAS, it's a kind of a great event. A lot of displays and activities, booths, and just kind of a great time for the community to come together. So I know that we do need some volunteers to man telescopes and the SAS booth there from 10 to 4 p.m.
I'm planning to
Can I
be
butt
there.
in for a moment, Tim?
Yeah.
I know that Angibur is looking for another event to come to, and I would say between Friday and Saturday, Friday at Delta College is probably going to be more promising than Saturday. Am I correct on that?
Absolutely. So, Angber, you definitely can join us at Delta College. And if you don't know exactly where we set up,
I sent them a map with the newsletter.
Good,
It has a map
good.
on the back. And also, Earth Day at Victory Park would be another event that you could attend, Angibur. That would be right inside the deadline, and we're not strict on the deadline. So either of those would work for the event for this.
Plus, I would give you a chance to look through the solar telescopes again.
Yes.
Tim, can you hear me? This
Yeah,
is
hi, Karen.
Karen.
Hi, Karen.
If
Hi,
you
Karen.
give me a call, I could probably show up to Delta College tomorrow.
Okay. Okay, wonderful.
I'm ready to come out and about, I think.
Okay.
We'd love to see you there, Karen.
Good to see you,
Give me a
Karen.
call, please. I'm not sure where you set up, so you'll have to give me a call.
Yeah, I'll do that.
All right.
Thanks, Karen. Okay. Then looking to May, we've got a star party on May 4th. We'll determine what site we go to at that time. May 9th is our general meeting. We'll be back at the Harmony Grove Lab at San Joaquin County Office of Ed. Eric's got a great presentation. I'm really looking forward to introduction to astrophotography that Eric's going to present. And then May 18th, everybody put the May 18th on your calendar. Come out to Oak Grove Park in the late afternoon. We're going to have our annual club potluck. The Nature Center will be open with activities, and then we have astronomy in the park that evening. So May 18th, that's a Saturday evening or afternoon. So, okay, then moving on. Unfortunately, Bill jumped off the meeting here, but we want to thank Bill for securing a $350 donation from PG&E for his community service. So, Bill, if you're going to watch the recording of this, thank you very much. It's a great thing, and the club really appreciates it. So, okay, and then moving on, I think you all know that our 75th anniversary is coming up. And so Doug is working on getting some t-shirts printed up for us, and he's going to be taking pre-orders of those t-shirts. And so be looking for some announcements either in the newsletter or emails of how you can pre-order your size and quantity and the pricing. So. Okay, on a little bit of a sad note, well, not a little bit, a very sad note with a sad heart, we lost our member Joe Soares in January. Joe and Karen have been members of the club for a very long time, since before I started, and so we are going to really miss Joe, and he was always a great guy to just hang out with and talk with, and great sense of humor. So Karen, we reach out to you and with our deepest sympathy, and know that we've got some great memories of Joe from the events and outings that he participated in with our club. So and then I've got a couple of slides here that I just wanted to share. I grabbed some photographs off the media. None of these are personal photographs, but the solar eclipse on Monday, and I just thought I'd share them with you. We are planning at our June meeting to have our members show and share their stories and photographs. So be preparing for that. So I just wanted to, while it's fresh in everyone's mind, kind of share a couple of photographs here. So please jump in and comment or talk about these photographs. I'll kind of talk about them as I see. The one in the upper left is a view from the International Space Station of the moon's shadow crossing. I'm not sure about whereabouts in the United States that's crossing, but kind of thought that was a really unique view of the eclipse.
Tim, I think that ISS was seeing it when it was up near Maine.
Okay.
There's a similar image to that one taken from one of the Starlink satellites. I guess they have a camera on board, a pretty cool image as well. So if you have time, you might want to try and find that one online.
Oh, okay. Yeah, that'd be interesting to see. The photograph of the two planes, acrobatic planes in the upper right, are the Red Bull acrobatic airplanes that they staged this shot specifically to get this kind of a cool image and great photograph, I thought. And then the one in the lower left is just purely an amateur, like any one of us, just using his DSLR and a zoom lens and a solar filter. The photograph in the lower right, I found, I saw it on the news broadcast of the eclipse viewing in Washington, D.C. And I kind of thought it was kind of important to recognize how so much of our country with opinions and divisions can kind of create all these divisions within our communities or our, but the solar eclipse, a lot of astronomical events kind of bring us together because it really reminds us that we are really all one race on this planet. We've got to all get along. So I thought that image was, I depicted that pretty well. This next set of slides is kind of a cool one in the upper left showing the prominences. And I'm hoping that some of our club members, and I know Eric, the photograph that you took, you shared with us already, and Michael, the photograph that you shared with us, probably are even better than this, showing the prominences and the flares right at totality. So
Yeah, I think I have a similar one on the upper left there that you can see on our club's Facebook page. So you can go to our StocktonAstro.org website, and there's a link to the Facebook page where you can take a look at that.
yeah, this photograph in the center, I wanted to ask you guys, is that a sunspot that I'm seeing in the middle of the sun? Were there spots visible?
Yeah, there was a one or two. Yeah,
There was two of them.
yeah,
And there was a pretty prominent one towards the center. Yes.
that looks accurate. Yeah.
Yeah. Kind of also shows that even in cloudy sky conditions, you can still see a great image of a great view of the eclipse.
You can.
The one on the upper right was an amateur photographer that captured this airplane jet going across the eclipse right at the perfect timing. So kind of really picturesque. And I think that was pretty popular on the media as well.
That seems almost too good to be true. that would.
Yeah,
I guess-
we need to check whether that was photoshopped or not.
I think there might be some photoshopping going on, even on that Red Bull one. But
Yeah.
maybe it's an incredible coincidence. But gosh, that's luck then.
I agree. The lower left again, kind of a cool picture of the Statue of Liberty, and I guess was Washington D.C. wouldn't have been in, or New York City wasn't on the path of totality, so this was a partial eclipse, right?
Correct.
Yeah. And then the one with the weather vane, and some photographers put together this sequence. I kind of thought was really nice. I love sequences of eclipses so you can see the progression and the movement of the moon across the sun. The one in the lower right, I think probably from a cloudy area, who knows? But again, the eclipse was visible through the clouds. So. And I think we saw that, Jerry, back in October for the annular eclipse here in Stockton. We had kind of cloudy skies, and they were kind of popping in and out during the eclipse was popping in and out of the clouds. It was you could still see it through the clouds. So, well, okay. That kind of winds up our meeting. Unless there's somebody that has something they want to bring up or comment on. Before we close out, I will remind you that if you have any images or story or anything you'd like to share in the newsletter, or Eric is actually going to be setting up a site on the internet that we can put our images and share privately amongst ourselves. So kind of our own astro imaging corner. Look for that to progress and come along in the future. Well, okay.
Sounds good.
Again, thank you so much for being at the meeting this evening, and look forward to seeing you all maybe this weekend or at the Earth Day Festival on the 21st.
Yep, I'll be there.
All righty.
Thank you, Tim.
Thank you all. Good
Have a
evening.
good night, guys.
Good night.
Good
Good
evening.
night. Yep.
Good night.